In this lecture, we would explore the concept of transpose of a linear transformation. Now, what in fact happens is that corresponding to a linear transformation from a from a linear space into another, there exists a unique linear transformation between their duals in the reverse order. Now this is the one that we are going to explore. So I think I have revealed the secrets, but let us try to understand this problem by going to an example. Before that, our general assumptions will be that V and W are finite dimensional linear spaces over F with the dimension of V equal to N and dimension of W equal to M. And V prime and W prime are the dual spaces of V, by which we mean the space of all linear functionals on V and W respectively. Then dimension of V prime equal to N, which is the dimension of V itself, and the dimension of W prime equal to M, which is again the dimension of W itself. Now we start with a T belonging to the space of all linear transformations from V to W, designated by LV. So T belongs to LV. So this is the general background that we have. What we do is, before we start exploring the theory, we look at some example. And very interesting. A simple example. Very interesting one. Let R2 over R, it's a two-dimensional. Now let a typical element be X be designated by X1, X2, which is essentially where E1, E2 are the standard bases, where E1 equal to standard basis. That's your X. Now we take both the domain space and the range space as V itself. So we are considering linear transformations from R2 to R2. Okay. Suppose G belongs to V. Then G of X equal to, G is linear, therefore X1 into G B1 plus X2 into G B2. So let me write psi 1 equal to GE1 and psi 2 equal to GE2. So G is essentially represented by psi 1, psi 2. in R2. That's the representation that you have for this with reference to the standard basis that you have chosen for V, and there is a induced basis, what you call the dual basis on V prime, which is again, which will make it even, which will make it a replica of R2. Okay, so we shall not look into that at the moment, but this is what we get. Now let P belong to LB be defined by P of equal to A11 x1 plus A12 x2, comma A21 okay. So this is the linear transformation that we consider, where Aij so that fixes the linear transformation. Now you see that if you were to consider the matrix representation of T, the matrix representation of T is then from R2 to R2 represented by the matrix A11 where B is the standard basis. Okay. Now let us compute for some G V prime. Let us compute G of T x. Now G of Tx is then equal to, what is Tx? Tx is given by this one. Therefore, G operation is essentially multiplying by psi 1 and psi 2 the components and adding. So G of Tx is then equal to psi 1 into or I will put it this way. Right. That is G of Tx. Now this I rewrite as follows. See, I rewrite this as A11 psi 1 plus A12 A21 psi A21 psi 2 times x2. Okay. So it is actually some scalar multiplying x1 plus some scalar multiplying x2. So this I can write as therefore now you see that there is a new transformation that we denote it by t1. Let t prime be defined by t prime of which is essentially right. Okay. This in fact I can write as the following. Side 2. This I can write in this way. Then what you observe, this is an element of t prime of g. It is a g that we have started with, is now defined okay. And this is true for, so corresponding to each psi 1, psi 2 that you see, psi 1, psi 2 actually fixes g, and its image under t prime is taken as eta 1, eta 2, where it is determined in terms of psi 1 and psi 2. Okay. Therefore, what you have, so let me write that. So I'll just take out the basics which all of you know. So I don't think I should need this to be detailed here. But as and when we require, I will again recall it. So there is no problem. Okay. Therefore, what you get? So I can write the following. So I have g of tx. This is equal to x2, okay, and this I write as, this is equal to t prime eta acting over t prime g acting over x. Okay. So this is true for every every G belonging to V prime, which is equal to R2 prime. That's the dual space of R2. So you see that there is a linear transformation and T prime is linear. One can verify that T prime is linear. So you shall do in general. T prime is linear because you see that after T prime is represented by A11, A21, A12, A22. Multiplication of psi1 and psi2. Therefore, it's a linear transformation. Okay. So corresponding to G for each Aij belonging to R2, there exists a T prime belonging to L R2 prime which is represented by the transpose interchanges rows and columns. Of T. Possibly this matrix transformation is with respect to the dual basis. I put a question up here, that is something to investigate. That's a guess. It's a wild guess I am making. Because in this example, what you see is that we started with the standard basis, and what is the dual basis of, because V prime itself is again R2 with the dual basis given by the same E1 and E2 for that. Okay, so that is the consideration that we have. So we are guessing that this would be true. Possibly this matrix representation is with respect to the dual basis. Let me show you with one expression of T prime is dual basis. Okay, so that example throws some light into the sort of things to come. Now let us try to explore this further in the general scenario. Okay, so let me take out this. I am going to bring in the diagram to explain things out, and then we will try to explore it in depth. Okay. So we have now the general scenario that I have described. We have V, we have W, we have F here, we place F here, then you have, this is n dimensional, this is n dimensional, that's what I have. I have V prime, and here W prime. This is also n dimensional, this is also. What I have is this T belongs to LV. So this maps V to T. Let's see it. Now what I do is I take a G belonging to W. G belongs to W prime. In the example, they were all V prime, so both the domain and range of the linear transformation was considered V, so there is nothing to consider here. Therefore, what you have is this. Now, G maps TV to a scalar. What is that? G is a, G belongs to W. G is a linear functional over W, therefore it can legitimately act over Fp or carry Fp to a scalar here. And all operations are linear here. Okay? So what I try to do is try to conceive GTV as some F I write this as F. Okay? So this is the definition of F. What is F? So I write this as F. Now let me just be quite vague here. So F is somewhere. I just put it. So I have V here, V is mapped into TV, G carries it to GTV, a scalar here. Now I define a functional on V which is possible by FV equal to G of TV. So my definition is this. Where does F belong to? Now you see that F defines a functional on T here because F is a scalar. So F defines a functional. I have not made any tall claims. I am yet to make some claims. So clearly it defines a function, it is defined for all V. So it is defined for all V belonging to V. For any V you have the corresponding TV, you look at the mapping by G of that vector, it gives a scalar, that scalar you work back through your V and reach where you reach, you get a functional defined. And it is defined for all V, so there is a functional defined in this way, this is well defined. There is no problem. Now the question that you ask is this: Is f linear? This is the first question that you raise. Okay, let us investigate this. So if it is linear, this is what you have to see. What is this? F of C V1 plus V2, is this equal to C times F of this is the question that we are asking for V1, V2. Is this really true? Let us investigate this. So what is by definition f of this is equal to, what is the definition? The definition is in terms of G. It is G of T acting over. Now, why do you suspect this to be linear? The reason is that, see, you are working in a linear space, your D is linear, G is linear, therefore we expect the composition also to get the property. It is well defined. Okay, now this is equal to what you get, T is linear, therefore you have G of T and this is equal to, by the definition of a function, you don't need much here, and the fact that G is linear, you have G is, this is G of but what is this? This C comes out. So this is equal to C times but what is that by definition of F? This is equal to C times this is exactly what we wanted to prove. Okay, which implies so that is done. Therefore, in this figure, you see that, see, this is the space of all functionals on so the place of F is here. Okay. Hence, E prime. Okay. So, corresponding to G belonging to W prime, there exists a uniquely determined F belonging to V prime. Therefore, V1. Okay, let me just take out this. I don't need this anymore. Therefore, So V is a linear function. This is important. Hence, we shall define mapping we shall define a mapping from W prime to V prime designated with T prime by E of T prime of F is equal to T prime of another F of T that is done. So this is the done. Or in other words, I can write this T prime of G that is how T and T prime are related. But that's just a matter. Is T prime linear? Because linearity is there at all stages and at all levels, we expect P prime so defined also to be linear. So what you have to do? You have to check this again. P prime of CG1 plus G2 is it equal to this is what you are asking for. Is this really true? Let us investigate it. So what is T prime CG1 plus G2 of V? This by definition is CG1 plus G2 of T. Now you apply linearity. Okay. What is this? This is equal to simply function property. CG1 which is again C times G2 T. And what is that? That by definition is equal to C times F1V P prime of G1 equal to F2 What does this mean? This implies P prime of C times so this is what we have proved. And what does it mean? Which implies P prime belongs to L W B. Just think, the two things we just changed. Therefore, P prime is a linear transformation from W to B. That's it. Yes. Okay, what next? So, corresponding to every linear transformation T from V to W, there exists a corresponding uniquely determined linear transformation from W prime to V prime. And related by the relation that P prime of G acting over V is equal to G TV. So let us write down. That is transformation P prime belonging to L W prime V prime such that, or the definition of that is the following, that is P prime of G acting over V equal to G acting over this is how T prime is defined. But T prime is defined from W prime to V prime. Now you see T prime of G will be a linear functional on V, that is it belongs to V prime. It acts on V to give a scalar, and that scalar is precisely obtained by the action of G on the image of V under. Okay, so this defines the linear transformation T. Now P prime belonging to reduced by P this is the concept of. I think this diagram should make things very clear. Okay, what it is all about. So that's the dual of T. Now naturally there is a question, there is something that we have observed in that example. What was that? There is an induced linear transformation from V prime to V prime, okay, represented by the transpose matrix, the transpose of the matrix of T with respect to the the matrix of T is given in terms of the what is called the standard basis for R2. And incidentally, we also observed that this matrix representation appears to be with respect to the standard basis on V prime. And the standard basis on V prime is essentially the dual basis on V prime. Now if you want to make it bit more elaborate, then it's all that you need is examine this problem. Look at this problem. I leave the computations to you. We take V to be R2. Now let us take the standard basis. So P3 tilde. So you call this respectively B, V and VW respectively. Okay. Now they consider the linear transformation. Equal to and this gives the representation for T as okay. This is the matrix. Then show that E prime belonging to L standard basis for each of the dual basis for the standard base of V and respectively is given by matrix the transpose of so this is the representation for P prime. Okay, now this is essentially P prime, the matrix of P prime and this the important aspect is that we are using the dual basis. So let us now formalize this in the general scenario. This is just observations that you make on the examples, and now you conjecture those observations into theorems and then try to prove it. Okay, let us investigate this. Okay. So let V and W be linear spaces over F of finite dimension. Then we take a basis. We define by BV Bn, and then the dual basis for designate by F1, where we have F5 Similarly, BW we designated by N, and B prime W prime, that's an order basis for this. GM, where GI so these are the dual bases that we have. Now we look at we are now exploring the matrix, the relation between the matrices, matrix representations of V and W. So let me just write here a timetable. Matrix representation of that. So let T be given from as a linear transformation from V to W. So it is in LVW. Defined by, you know that a linear transformation on V from V to W is defined by prescribing the images of V1, V2, etc. Vn. So let us do that by defined by P of, should be careful about indices. Well, TVJ is an element of W. W has basis given by W1, W2, etc. Wm. It's an ordered basis. And in terms of that, TVJ has a unique representation as a linear combination. And that is written by this, and that uniquely fixes the AIGs. Now, how many such scalars are there? In all, there are mn scalars. Okay. Then we know from what we have done already that the matrix representation of T with respect to dV is given by AIG. It is an so you have so I run from 1 to m. Okay. So this is the representing matrix, which is an m by n matrix. Now, as we have seen, T prime belongs to T prime. We want to see, we know that it has a representation like this. So let the matrix representation T prime be defined by what you have. To see what happens to the dual basis. So T Gj or T prime of Gj equal to sigma I equal to 1 to n F1 for okay. This is an efficient application. Now, what we want to find out is what is the relation between BIS and AIS. Then, which is an n by m. That means you have 1 less than or equal to I less than or equal to n. So we know that if this is represented by an m by n matrix, then T prime is represented by an n by m matrix with respect to the dual matrix. I mean, that is obvious. Okay. So you have got here AIJs are mn scalars. So also BIJs are mn scalars. So you are asking the simple question: how Bij's are dependent on Aij's. Now this is the basic question that we ask, or how these two representations are related. That's the question. This is the basic question. Let us explore this. Okay. So we go to the basic definition of T prime and then work from the connection between the two. Okay. It's a wonderful piece of mathematics that you have seen. Okay. Let us compute the following. We compute the following. We compute GK of, we call our picture this is equal to G of P, which is equal to P prime G acting over that's how it is given. So this picture we will keep until we complete the story. Okay. Right. Now what we do is we compute T, that is the action of GK over TBJ. Okay, so V1, V2, etc. Vn is here. You are looking at the images of that. On that we are looking at the action of GK. So let us compute this. What is this? This is equal to sigma I equal to 1 to n. By definition, this is Aij GK Wi. This is what you have. I am just using the definition here. Okay. Just using the definition. Okay. Because this is equal to so let me write here P prime of Let me write here. T prime of GK this is equal to GK of T and this is given by this. And it just passes through one step, namely you are writing TVJ. TVJ is written as a linear combination of TVJ is equal to sigma I equal to 1 to m Aij Wi. Then you are applying G on that. When you apply GK on that, the GK will migrate because GK is linear. Okay, so this comes from, I just write here, you have TVJ, this is equal to sigma Aij Wi, therefore GK TVJ equal to sigma GK of that's how it comes. So this you are using the linearity of GK. And this, let us work it out. What is GK or WI? GK of WI is equal to sigma I equal to 1 to m Aij. So this part GK of WI, because it is the dual base, this is wherever we use the fact that dki, which is equal to, when I equal to k you get 1, otherwise 0, therefore you get a. That's a computation. So we keep this aside. Now let us calculate this. GK of TVJ is also equal to T prime GK of TVJ, which is equal to, by definition, it is sigma Bik Fi That's the definition. So simply writing down the definition that this relation T prime of Gj equal to this one, J is replaced by K, that's the only difference that we have. Therefore, if you compute this is equal to, this is equal to sigma Bik Fi of Gj. Then of course we have from here the summation is from I equal to 1 to m, I equal to 1 to m. And Fi Vj you can write as delta Ij because that's again the duality connection. So this you have I equal to 1 to m Bik delta Ij. Therefore, what you get? This is equal to, see, you are summing over I. So when I equal to j, you get 1, otherwise you get 0. So you get b. Therefore you have two results. One is this one, the other one is this. So they are equal. Therefore, AKJ, this is equal to GK of T Vj, which is equal to T prime GK of Vj, and that we have computed. This is equal to okay. Therefore, what do you get? This implies or in other words, what this means that B is equal to A prime the transpose of so that completes the proof. Okay, so what you have is this, that the matrix representation of T with respect to B, V or T prime, B prime, W prime, B prime, V prime is given by the matrix representation of T transpose. Okay? This is the relation. So this time stands for transpose. Okay? So that completes the proof of what we were trying to do. And that connects the dual operator with the original operator when we are trying to seek the representations in terms of a certain ordered basis chosen for the domain and range. Then with respect to the dual basis for the dual spaces, the matrix representation of the dual map is given by the transpose of the original matrix. Excellent. Okay, I think I'll stop here. Thank you very much.